Yeah. So let me share the screen. Hi. Okay, so that day I was doing this, right? Remember?
Yes, yes.
I was trying to get the Newtonian equation. So, I mean, I was missing something, but it's very trivial actually. What happens is, see, I have this thing, now, this equation. Now, let me, okay, so I have got this. Now, let me break this up into, okay, so let me do the following. I will, let me remove this. Okay, so till here it was okay. Fine. Now the only thing which was required was, now this was can be written as d2x alpha by dt square plus there will be three types of terms, gamma alpha 0 0 and dx 0 by dt is 1 plus twice gamma alpha 0 beta dx beta by dt. You know why it is twice and so on, right? Because of the symmetry of the gamma. Is it okay?
Yes.
Okay.
Yes.
Plus gamma alpha beta alpha beta gamma dx beta by dt dx gamma by dt. Now all what you need to see is that, see, these are all velocity dependent terms. So in the limit of non-relativistic things, these things can be neglected. Okay. And so we are left with only d2x alpha by dt square plus gamma, I mean, this is equal to 0. 0, 0 is equal to 0. And this is what turns out to be, which we already showed that day, dx alpha, d2x alpha by dt square plus half g h00 comma alpha equal to 0. I mean, this term was 0 because this is 0. That's what I missed that day. And then everything else follows. Is this all right? I mean, should I do it again?
No
Why?
problem.
Yeah.
Pardon?
It's fine.
It's
No
all
problem.
Can you explain the limit of non-relativistic? So why are the
Oh, I mean, it's basically saying that, not only you are saying that Hij is much less than 1, you also have V much less than C, right?
Okay, okay,
So
okay.
that is why the velocity term will drop away.
Fine, fine.
Okay. So that is the thing. Okay, so let me continue today further. Yeah. So let me start a new one. Okay. Yeah. So right. Yeah. Okay, so now what we say, okay, so we actually came up the following. We already showed that in weak field limit, G00 is equal to 1 plus 2, the gravitational potential. And if you actually put in the value of C and so on, it will turn out to be G00 equal to 1 plus 2 phi by C square. You see, the gravitational potential has the dimensions of C square because gravitational potential energy will have dimensions of energy. So it's mc square. And gravitational potential energy is mass into gravitational potential. So mass cancels out. So this is what is the thing. Okay. So in the weak field limit, this is so. Fine. Now, the other thing which one sees that, so the geodesic equation d2xi by ds square plus gamma I jk dxj dx ds square dxk by ds is equal to 0. This tells me that given the form of gamma, I know how the velocity will evolve. Now, gamma can be non-trivial, non-zero, either because it is a nonlinear coordinate system even in flat space-time, just like polar coordinates, or it can be genuinely curved space-time, like a curved space on the surface of a sphere. You get it?
Yes.
Okay. Yeah. So in some sense, this equation, what it tells is the geometry tells the particle how to move. Okay. So the trajectory of the particle, it tells how the trajectory of the particle depends on the geometry or the coordinate system. Okay. It is just like in electromagnetic theory, if I have a given electric field, it will tell the charged particles how to move. Okay. So this is something like that. But now you can ask another question. What does the geometry, how does the geometry tell the field to evolve? Right? And in this context, I will recall the equation which I got that day, which is this thing. I got an equation, right? Where was it? Hey, this is for the, yeah, this one. So we had got the equation gamma j I j is equal to 1 by square root of minus g del by del xi square root of minus g. We had got this, correct? And we also showed from here that if we have if we have ai comma k, I mean semicolon k, the covariant derivative is equal to ai comma k plus gamma I k a j j. Okay, so just to keep just to keep it in the same spirit as that, let me call this J, 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 and I'll call this dummy index as I. Is this okay? This is the standard definition of covariant derivative. And I said that for covariant divergence, this is okay. And for covariant divergence, I have AJ semicolon J is equal to AJ comma J plus gamma J I J AI. And this meant that this is equal to I multiply by root minus G and divide by root minus G del AJ by del XJ plus what is this? Sorry. This is what it is. Okay. This is okay, right? I've just made J equal to K.
Yeah.
Are you with me? Yeah.
Yes.
And then this
Yeah.
is equal to nothing else but square root of minus G del by del X. What am I doing? So since this is a dummy index, I can convert it to J. Okay. So let me just write that step also in between. So this is equal to square root of minus G by square root of minus G del AJ by del XJ plus 1 by square root of minus G del by del XJ square root of minus G AJ. And so I write this as 1 by square root of minus G del by del XJ square root of minus G AJ. All right. So this is the expression for divergence. Physicists are greedy and they now want covariant divergence of a tensor. Okay. So let us now go for that because, all your equations involve tensors. We saw that for physically relevant equations with tensors. And so since there are differential equations, you need covariant derivatives. And so let us consider a tensor, a second rank contravariant tensor. T I J. Okay. Now this, I know that semicolon K will be equal to T I J comma K plus it is gamma. I will first take the I here and I will retain the second one which is J here. Since there is to be a something here, I'll put an A and the derivative here. And similarly, it's gamma. Now I will retain, now J was retained here in the second term. Now I will be retained in its place in the second term. And I will put A. So the other thing J comes here and this is the derivative. Fine?
Yes.
Okay. Now I want to get the covariant divergence. Now, what is the covariant divergence? In flat space-time, I mean, I need not write flat Minkowski. In Minkowski, I have divergence is Tij, comma J. Right? Remember when I did Maxwell's equations, I had electromagnetic field tensor and I had put this. Remember?
Yes.
Yes.
Yes. Okay. No. So I just write down the covariant divergence. So for covariant divergence, I have got Tij semicolon j is equal to Tij comma j, and what I will do is I'll put k equal to j plus gamma I a j T a j plus gamma j a. Now k equal to j, so I'll put j and then TIA. All right. And now you see that this has got that gamma JAJ term. And so I will write this as del Tij by del xj plus gamma IAJ. This I will just leave it as it is. Plus, now this quantity I will write as 1 by square root of minus g del by del xa of square root of minus g TIA. And so now this is equal to square root of minus g by square root of minus g del Tij by del xj plus, I will put this here first, 1 by square root of minus g del by del xj square root of minus g Tij, because A or J is a dummy index here. So I have replaced here, okay, so I have replaced A equal to J in this one. Okay. And then I have this thing coming here plus plus this same thing, gamma IAJ TAJ. And this can be written as 1 by square root of minus g del by del xj square root of minus g Tij plus gamma IAJ TAJ is equal to the covariant divergence of J. All right.
Yeah.
This quantity has a lot of similarity with this quantity. All right. So just to recall, AJ semicolon J is equal to square root of minus G del by del xj square root of minus G AJ. But this has an additional term. Now let us look at this additional term. We know that gamma IAJ is symmetric in AJ interchange. All right? Okay?
Yeah.
Okay. Now this TAJ, I can write it as TAJ by 2 plus T JA by 2 minus T JA by 2 plus T AJ by 2. I just added and subtracted the after interchanging J and A. Remember, T need not be symmetric. All right.
Yeah.
I just added. And so this is equal to half TAJ plus TJA plus TAJ minus TJA half. Now, if I may, so if I put this as SAJ and I write it this as AAJ, I can write it as half SAJ plus half AAJ. Correct?
Yes.
Now, if I interchange A and J, this will go to this and this will go to this. And it's a plus sign, which means interchanging A and J, S will not change. So S is the symmetric part. That's why I put S.
Yeah.
Whereas here, if I interchange I and J, it picks up a minus sign. So this is the antisymmetric part. Okay?
Yeah.
So now I write this as TAJ TIJ semicolon J is equal to 1 by square root of minus G del by del xj square root of minus GTIJ plus gamma I A J half SAJ plus half AAJ. I just substitute for TIJ. Okay? Okay, I just substituted it here because this is basically TAJ. Hey, are you with me?
Yeah.
Yes.
Yeah.
Yes,
Okay. Okay. And now, so I can write this as another interesting way. I can write it as 1 by square root of minus G del by del xj square root of minus GTIJ plus half gamma IAJ SAJ plus gamma IAJ half AAJ. What is this equal to?
0.
0. Why?
Contracting a symmetric.
No,
Product
not
of
contracting.
symmetric
See,
and
it is
antisymmetric.
gamma IAJ AAJ is equal to, I will just interchange A and J because they are dummy indices. So this is gamma IJA AJA. But now this is equal to gamma IAJ, which is symmetric, and then a minus sign AAJ. All right?
Yes.
So this is equal to minus of itself. So gamma IAJ AAJ is equal to 0. This is always there, even in matrix. If you multiply a symmetric matrix to an antisymmetric matrix and contract it, it is 0. Right?
Yes.
Okay, so that is the same thing. So basically what it says is, so okay, so basically we have Tij semicolon j is equal to 1 square root of minus g del by del xj square root of minus g Tij plus the gamma Iaj, the symmetric part of, oh, actually, oh yeah. I mean, I will, this whole thing I will call it. So I will not have that half here. I mean, just a question of what is S. Okay, so this is how it will be. Okay, so the one which this portion goes exactly like the vector, contravariant vector. The only thing which spoils is symmetric part. Now we say that suppose I have a tensor, say TR IJ, which is antisymmetric. This implies that the symmetric part equal to 0, which means there is no such term for this. So, if Rij is antisymmetric, then Rij semicolon j, it goes exactly like a contravariant vector expression for that. All right?
Yes,
Yes.
yes.
Okay. Now can you use it anywhere? And this was the reason I made the whole detour of electrodynamics. You know that Maxwell's equations in curved spacetime are this, some 4 pi, whatever. We had derived this.
Yes.
We said that in flat spacetime, it is Fij, comma j is equal to jj. This is a tensor equation. I mean, so you can always write as a covariant thing, but this is a tensor equation. So this equation remains same in any system. So this is the general equation in curved spacetime. And now this quantity is an antisymmetric tensor. It means that these pair of Maxwell's equations can be written as 1 by square root of minus g del by del xj square root of minus g Fij is equal to it's ji. Okay, so this is the form of Maxwell's equation, that second pair of Maxwell's equation in curved spacetime. All right?
Yes.
Yes.
Okay. So now what does this show? Just now I showed how a non-trivial geometry modifies the trajectory of the particle, which was the geodesic equation. Now it tells me how the non-trivial geometry modifies the field configuration. Okay.
Yes.
Okay, because Fij has got the information about, so I mean, if you want to write it explicitly, you can write Fij is equal to G AI G Bj, sorry, G AI G Bj Fab, and this is equal to GAI GBJ del, I mean, which was it? Del AB by del X? I think this is what it was. But is it correct what I have written? In a general spacetime?
I think A by XB.
AA, is it? Okay.
Yeah.
But is it correct?
I guess it is.
For a general spacetime, and A is a vector. I've used a partial derivative. Shouldn't I use a covariant derivative?
I couldn't get the question.
What I'm saying is, I am writing this for a more general spacetime.
Yeah.
I am writing f as this one. But then I know that for for physically valid equations, it should not be partial derivative of a vector, but covariant derivative of a vector, because partial derivative is not a tensor.
Yeah, we need to write it in covariant.
Okay. The answer is no, which I already showed. I'll tell you why.
The
You're right.
difference
So I will write
is-
it as GAI, GBJ, AA covariant derivative B minus AB covariant derivative A. This is GAI, GBJ, AA, comma B minus gamma C A C A B minus A B comma A minus plus gamma C B A A C.
Yes.
Yeah, it cancels
But
out.
since they are symmetric, these two cancel out. So although strictly you have to use covariant derivative, that extra portion gets cancelled, so I can still write the partial derivative. Alternatively, del AA by del XB is not a tensor. Del AB by del XA is not a tensor, but the difference between them is a tensor because the non-tensorial nature cancels out. The non-tensorial portion cancels out. Okay?
Yes.
Okay. And that is why I can. So once I write this, now I can write, so the entire thing can be written, although a bit complicated, in this one. So in terms of A, I can write the Maxwell's equation. Of course, now components of G will start affecting the equation, but that's something which you can't avoid. Okay, so this is an example of why covariant divergence is useful. All right?
Yes.
Yes.
Okay.
Yes.
So the other pair of Maxwell's equations were I, J, comma K plus F, K, I, comma J plus F, J, K, comma I equal to 0 in flat spacetime. Okay. Since in flat spacetime, these are in flat spacetime, this is Fij semicolon K plus Fki semicolon J plus Fjk semicolon I equal to 0. But now it is a tensor equation. So in any space-time, I have this equation. All right? Okay.
Yes.
Yes.
But now again, there is an interesting thing here. I have Fij semicolon K is equal to Fij comma K minus gamma A F A J I K minus gamma A F I A J K F K I semicolon J is equal to F K I comma J minus gamma A F A I J K minus gamma A F K A J I. I mean, it's just the same formula I have used, no? In a cyclic thing, it is there now. Now, this is J K semicolon I is equal to F jk comma I minus gamma a f a k I j minus gamma a f j a k and then I. Okay? I've just written it for each of them. And so the left-hand side is the sum of all this. And this should be 0. All right? This plus this plus this is the Maxwell's equation, this one. Now look at this one. You have I gamma a I k. Yes, okay. So now let us, now let us look at this term. This is AJ, this is JA. So I can put a minus sign and put an AJ. Similarly, I can, sorry, not my extra minus or plus sign, again plus sign AK. And again a plus sign AI. And then I find since J and K are symmetric in gamma, this cancels out, this cancels out, and this cancels out. So it boils down to exactly like the flat space equation. I. So just like that other thing which I was telling about the derivative of A, you need not put covariant. In these Maxwell's equations also, even if you put a partial derivative, it is okay because the non-tensorial portion cancels out. Are you with me?
Yeah.
Yes.
Yeah.
So we have been able to write Maxwell's equations in curved spacetime. For example, suppose I have a gravitating object and I keep a charged particle near it. From here, in principle, I can get what is the configuration of the field.
Yes.
Ah.
So that electric field will also be affected by this geometry, isn't it? Like electric
Yeah,
field will
actually, there
get
is
bent.
another thing. So, okay. Yeah, you could ask me. See, the question is, what is electric field? You know, you have these electric field as, I mean, the F mu nu is components are this one, no? But I don't know whether I'll have time to come to that. Actually, if suppose you want to write the alpha component of the electric field, this is basically F A I U I. This is what it is. When UI is static, then this is the usual electric field thing. So if suppose I have, yeah, so this is what it is. I mean, so this is the, okay. And then the eighth component of B is F tilde AIUI. Be a plus minus sign, but this is what it is. I mean, are you getting it? See, you know that if suppose you have a flat space time, then clearly this U lower I is, okay, so this will be equal to what? So, okay, I'll put it alpha because electric and magnetic field are only spatial components. Okay. And so this is equal to minus F A0. Sorry, no. Plus F no, not again alpha here, plus alpha beta u beta, right?
Yeah.
And this, so when you have a frame which is not moving, which is static, then u0 is 1 and this is 0. So it boils down to f of alpha 0, which is what you get in standard electrodynamics, that the zeroth column and row of f mu nu of Fij are the electric fields. Okay? I mean, are you with me?
Yes, yes, yes. Yeah, I was saying that like photons that light get deflected, you can show that this electric field also get deflected under the space-time. If you
Oh,
ever
yeah. So you actually, okay, I understand. So you write this and then put it in the Maxwell's equation and explicitly solve it. You will get that the electric field. So I'm not sure, but if suppose you have a massive body and you have a charged particle, the electric field is not like this, but there is some bending like this. I mean, you
yeah,
can actually work it out as an exercise. It's a bit involved, but you can do it. And in fact, once I have given this as a BSc project to some student, where you solve the Maxwell's equations numerically, the partial differential equations, and draw the electrical lines of forces.
okay.
Okay. So that will be very interesting. All right. I think I'll stop today. I'm too tired.
Like the four velocity you said, u0 becomes 1 and u beta becomes 0, right?
Yes, when it is static.
The space-time being static. What is static? Like the charge being static, right?
Yeah, charge is stationary. So you have a frame
Okay.
in which the charge is stationary. So the
Okay.
velocity of the charge is u0 equal to 1, u alpha equal to 0.
Okay.
Yes. Today, Snigdha has been extremely quiet, even more than usual.
No, Chris.
Okay. Hmm. Okay, so Adele, is it okay?
Yeah, yes.
Huh?
Yeah, it's okay.
I?
Am I audible?
Yeah.
Yeah, it is okay.
It is okay. Okay. Okay, Anil, Harish. Harish, I have to give you that thing, na? Okay, right now itself I'll send it to you in the
All
WhatsApp.
right.
Pardon?
Yes, all right.
And after 4 o'clock, right?
Yeah, anytime as you wish.
4:30?
Anytime after 4.
Yeah. Okay. Yeah.
All right.
Yeah. Okay. See you.
Okay, good night.
Bye.